So this is first week office hours, and there are a couple people here. So what problems do we have? So we're looking at MQ 0.1. What questions do we want to look at off of that?
14.
Number 14. What was that?
First one.
Number 1.
I need number 4.
Number 4.
And number 5.
And number 5. Great, we'll start there. Let's go ahead, let's do it in order. Let's do 1, 4, 5. So I don't know what number 1, what is number 1? Okay, let's see here. Number 1, a student titrates a sulfuric acid solution of unknown concentration with 1 molar sodium hydroxide. The titration requires 54.2 milliliters of the sodium hydroxide solution to completely neutralize 20 milliliters of sulfuric acid. What was the concentration of the sulfuric? So a whole bunch of words. Let's, one of the things that's most important, especially in Chem 129, is to critically read and work on our critical reading skills. So I'm just going to go ahead and write down the things that I think are important. 0.1 molarity sodium hydroxide and a question mark molarity of sulfuric acid. Right? So this is going to be, I'm going to color code this. I'm going to try not to drop this at the same time. So this is the thing that we're going to try and find. 20 milliliters. Okay, so we know that we have 20 milliliters of this. And we know we have 54.2 milliliters of this. And the question becomes, what's that unknown concentration? So this is what I call all of the explicit information. Right? This is all stuff that was just explicitly given to us in the problem. You could have someone who's never done a chemistry class just write down all the numbers. In chemical compounds, I know the formula, so I'm doing that. At that point, we have to say, okay, well, what's we know what we want to get to, what result we want, and the question becomes, and this is true for every problem in every class, you're given explicit information, you're given a place you want to get to, and there's something implied in the middle. And that implied thing in the middle is really what the question is about. It's like, hey, can you figure out the thing I'm trying to get you to think of? So, what's this trying to get us to think of? There's a couple different ways that our brain can approach this. First thing is I see an acid and a base, I'm thinking acid-base reaction. I also notice M1, V1, M2, V2, but it's 2 different chemical compounds, so I'm not going to do a dilution thing. Right? I might think that, but that M1, V1, M2, V2 was just for adding water, not for doing chemical reactions. What else could we possibly do? Is there anything else we could do? I think that's those are the only 2 things I think of. Did you think of anything else? So, given that it's not a dilution, I'm going to go ahead and write down the chemical reaction. Oh, another piece of important information in there. It specifically said this is a titration. Right? And there's implied information in saying it's a titration. We did titrations on 127. I think we did 1 or 2 on 128, but it was mostly a 127 thing. So there's important implied information. It assumes you know what a titration is and you know the important mathematical chemical process of a titration, doing the whole drips. And when we did titrations, when did we stop?
When it turned pink.
Why did we stop when it turned pink? You're right, we stopped when it turned pink when we did our titrations.
Doesn't the phenolphthalein indicate when it goes from an acid to a base?
Yes, it goes from acidic conditions to basic conditions. So the faintest color of pink is when? Not equilibrium, equal moles. It's when it's neutral.
Okay.
So the whole point of the titration is to find when our moles of acid is equal to our moles of base. So this gets us our first piece of implied information. It wasn't told to us in the problem. It's just the fact that it says a titration assumes we know right? Our moles of acid is neutralized by our moles of base. So this is an equal molar point with the stoichiometric ratio taken into account. That means we have to write down the chemical reaction, get it balanced. So, okay, we'll do this. So, H2SO4 aqueous plus NaOH aqueous. I'm going to go sideways because I didn't give myself space. Goes to H2O liquid plus Na2SO4 aqueous. I need to balance the chemical reaction to 2. So I've got a 2-to-1 mole ratio. Now, I know the concentration and volume of base, so I can do 0.1 times 54.2 milliliters.
No.
I'm not going to do millimoles to you yet. Times 1 liter, 1,000 milliliters. An important other thing to remember, I didn't do my units over here. Capital M, molarity, can be, also written as moles per liter. So capital M here, this is 0.1 molarity. I can write that down as 0.1 moles per liter. And I should write this down as moles of NaOH per liter of NaOH. This is milliliters of NaOH, converting to that. I can almost do that in my head. This is going to be 5.4 divided by 1,000, 0.0054. Yeah. So that's how many moles of sodium hydroxide I have. I know from my chemical reaction that 0.00542 moles of sodium hydroxide. I want my moles to be equal to each other. So I know that for every mole of sodium hydroxide, for every 2 moles of sodium hydroxide, there's 1 mole of sulfuric acid. Essentially what this says is I need twice as much sodium hydroxide or half as many moles of sulfuric acid because I've got that 1-to-2 ratio. 0.0054 is going to be 271. Have a calculator handy, double check my work. It's the beginning of the school year. My calculator brain's not totally reboot yet.
271, yeah.
So that gets me my moles of sulfuric acid needed. Right? That's how much H2SO4 we need to equally react. That's our equal molar. The question isn't asking for number of moles, though. It's asking for molarity. So what's the last thing we do to convert this to a molarity?
Divide by 20 milliliters.
Yep, divided by 20 milliliters. So we're going to take our 0.00271 moles. We're going to divide by 0.020 liters. I did the conversion from milliliters to liters in my head just by dividing by 1,000. Move the decimal place over by 3. And I will tell you, pretty soon in the quarter, I will introduce the idea of millimoles. It's just easier. Notice I had to divide by 1,000 here and then divide by 1,000 here. If I left everything in milliliters, I would have saved those 2 math steps and it still would have worked out because the divide by 1,000 would have canceled out eventually. But we'll worry about that in the future. Right now, we're just doing a review of stuff we've already seen. Does that make sense? Okay. Whose question was this? Okay. Good. I will show you another way to think about this. So this was the long kind of every step way. Now, what you'll notice is my moles of acid equaled my moles of base times the mole ratio. And this is part of where people accidentally, a lot of reactions we do are a 1-to-1 ratio. And so people try to do M1V1 equals M2V2. This happened a lot in 127 and it doesn't work. And it's because in 127, all of our reactions, not all, but most of our reactions were 1-to-1 mole ratios. And so it worked. I'm going to erase this stuff and write this in a slightly different way. Right? The key part from having this be a titration is that moles of acid equals moles of base times the mole ratio. Or you know, we could put the mole ratio on either side. What this allows us to say is molarity of acid times volume of acid, right? Molarity times volume gets me moles. Molarity of base times volume of base, that gets me moles. Times the mole ratio. Now, this works because of the definition of titration. This is not like M1, you notice I used particular subscripts. This is not like M1V1 equals M2V2, where you're just dumping water in and changing your volume and your concentration. This is a chemical reaction where we are defining a particular point of the chemical reaction where the moles of acid are equal to the moles of base reacted. So did you just try to do M1V1? Yeah, mole ratio, right? Because it's not just a dilution, it's a chemical reaction. We have to take that mole ratio into account. And the only reason it works is because we're specifically doing a titration to the equivalence point where the moles of acid and the moles of base are equal to each other. What we're going to do in this quarter, we're going to do titration calculations where we calculate every point on the curve. From whether you added 1 drop or if you added the amount to get to what we call the equivalence point. But again, weeks away from that. We'll get there. This is just a warm-up problem. Questions about this? I'm going to erase this. That was number 1. Let's go ahead and try number 4. Switching colors just to be dramatic. What is number 4?
Oh, here.
Okay, so number 4, we're going to do the same thing, right? I'm going to read this, but as I read it, you want to think, okay, what's the explicit information? What's the result we're looking for? What's the implied information missing between? Calculate the equilibrium concentration for the following reaction when 0.2 moles H2S is placed in an empty 1 liter container. In parentheses, this one will be hard to solve by hand. It is possible to solve by successive approximation if you simplify to a converging function. It might be better to use an online tool once you find the expression. And then it gives us a chemical reaction, and that's all it gives us. So it gives us, the chemical reaction is important. It gives us this chemical reaction, 2H2S goes to 2H2 plus S2. It gives us a K value, I'll go ahead and put a subscript EQ there, of 4.2 times 10 to the minus 6 at 1,100 Kelvin. And it says we've got H2 at, well, that's a weird H. H2S concentration initial 0.2 mole, 0.2 molar. Oh, no, that's not what it gives us. Sorry. I'm doing too many steps. I'm doing steps in my head. Let's not do that. It tells us H2S is equal to 0.2 moles initial in 1.0 liter. Okay, so that's all it gives us. And it says, figure out the equilibrium concentrations. What do we do? Did you get this one?
Yeah.
Okay.
So I watched the video on the successive approximation and I got all of that. but
Yeah.
I got to the point where we were starting this one and I couldn't
Yeah.
start it. I don't know why I couldn't start
I would just use an online solver for it. Like, so the thing is, you end up with like a cubic equation or something. It's just a pain to solve. And there's this trick where you can do it by hand, but
I did it by hand for a while.
yeah, no, it is.
It was great.
I'll mention the thing I like is if you do a search for Mathematica equation solver. That's my favorite equation solver online. Mathematica is software that I've used for years. I'm not sponsored by them. It's just software I've used. Their online solver is great. So if you just look for Mathematica equation solver, that's great. But let's set up the equation. A couple things to note. As long as the temperature isn't changing, this part doesn't matter, right? Equilibrium constant does change with temperature. We learned that in 128. If the temperature, nothing in the problem says the temperature changes, we're at a constant temperature, that part doesn't matter. It's just that KEQ is only valid at that temperature. So as long as temperature is not changing, temperature doesn't matter. You can see where I started doing part of this problem already. If you've got 0.2 moles in 1 liter, that gives you a concentration of 0.2 molarity moles per liter. Just do the division. It's nice that it's 1 liter, so it just works out really easy. Then we can go ahead and set this up. I'm going to start by writing down the expression for this. So my KEQ, I've got a specific value for my KEQ, but I also want the expression for this. These are all in gas state. That makes it easy because we can, we don't have pure solids or pure liquids. Products over reactants, I'm going to have my H2 squared. I'm going to have my S2 to the first. I'm going to divide by H2S squared. I'm going to include subscript EQ on all of these because that should be the equilibrium value, not the initial value. How do we get the equilibrium values? A subscript EQ on all of those. Is that what you're looking at?
Yeah, and I was just looking H2 squared because it's a coefficient.
Uh-huh. So the squared is from the fact that there's a coefficient out there. The squared is from the fact that there's a coefficient out there. What I should have done, I didn't give myself space for this, but you notice this expression implied, the use of the temperature implied. We weren't told what to do with temperature. It was just there. A lot of people were like, oh, it's just there as a trick. It's actually important that the temperature is constant. If you tried to look up the equilibrium constant for this thing at room temperature, it's not that value. So it's important that you know it's at a different temperature, so if you could try to look it up. This is a nice trick for teachers, because if I wanted to do a reaction that's not easy to look up, I just pick some weird temperature that's going to have a weird KEQ associated with it, and now you can't just like look it up. So it's a nice trick, but you don't need it after it's there. What we need to do is we need to figure out how we go from this initial state to this equilibrium state. That sounds like an equilibrium problem to me. So I'm going to go ahead and set up space for my equilibrium table. I'm going to have my 2H2S. Those two. Notice I'm using double arrows now because we've got equilibrium stuff going on. 2H2 plus S2. My initial is 0.2, 0, and 0. My change, since I've got zeros here, I could do a whole Q versus KEQ thing, but I know Q is 0 because I've got 0 products. I can't have 0 products. The reaction has to proceed at least a little bit forward in order to reach equilibrium. So I'm going to have minus 2x, because this is happening stoichiometrically. I'm going to lose 2 of that. I'm going to gain 2 of that. I'm going to gain 1 of that. So every bit that the reaction happens is some x value. And then I can go ahead and do 0.2 minus 2x, 2x, and x. This is my initial. This is my equilibrium values. So I can take these equilibrium values and I can plug them in here. I'm going to get, come on, 120, which class? 129, come on in. We're doing MQ 0.1. We're doing number 4 right now. Grab some chairs. I'm recording. Just hands up. Okay. I can plug these in. I'm going to have I don't have enough space here, but I'm going to go ahead and try to squunch it in. I'm going to have 2x squared. I'm going to have x, and I'm going to have 0.2 minus 2x squared equals 4.26 times 10 to the, no, 4.2 times 10 to the minus 6. So you can see, maybe you don't see, but I can see why I said, oh, this is a pain to solve. You end up with a cubic equation. Not an x squared equation, an x cubed equation. So let's go ahead and let's try using an online solver to do this. How did you solve it?
Are you gonna see my work?
Yeah, let's see your work. You did the x is small approximation.
Yeah.
That should work great. We're going to learn more about the x is small approximation. That works. The successive approximation method also works. Solving it explicitly also works. I'm kind of curious. So x is small approximation gets us 3.47 times 10. Is that 10 to the minus 5 or 10 to the minus 3? Point is, we've got to find some way, minus 3.
Yeah,
We've got to
3.
find some way to solve this thing. And there's kind of 3 different options. It recommends successive approximations, which is fine, you can do that. I'm recommending using an online solver because this isn't a math class, this is a chemistry class. I want you to think about the chemistry going on. Could we solve this with successive approximation, or even completing the cubes and solving a cubic equation? Sure, this isn't a math class though. You do that in a math class. Plus, let's use the tools we have available to us. Right now, when we're doing homework, we can totally use an online solver. And I encourage you to open it up. I'm curious how close or far away it is. So I'm gonna go ahead and do that. Let's see here. What's that?
Oh, when you have a second, we just had a question about the labs.
Oh yeah, sure. Here, let me do something real quick. I'm gonna pause this.
So when you assume it's small, what is it that we're assuming is small? What is that?
Yeah, so let's talk about the different ways. We've got someone who did the x is small. We've got someone who's tried the successive approximation. We've got someone plugging stuff into Wolfram. Let's talk about the x is small approximation and how that works, because that's actually what we're going to use most of the time this quarter. So we look at this and we say, look, the equilibrium constant is 4.2 times 10 to the minus 6. This gives me the idea that I'm going to make a really, really, really small amount of products, right? The equilibrium constant, since it's products over reactants, a small number usually means a small amount of products, which means this reaction is going to go forward a small amount, which means this x value that I'm subtracting and adding, I think that x value is going to be really small. If that x value is really small, what's a million plus 0.2? It's about 1 million. So if we have a big number, and we're adding or subtracting a small number to that big number, it's pretty much just the big number still. So the way we do that is we say, hey, this chunk here, approximately 0.2, right? 0.2, 0 plus 2x, 0 plus 0.2, 0 plus 0.5 is significant. 1 billion plus 0.5, that 0.5 doesn't matter. So this place where I've got a number and I'm subtracting something from it, I can approximate that to just be 0.2.
Do we also assume that the x in the numerator is 0?
No.
Oh.
The x on top, it's not that we're assuming the x is 0. We're assuming the x is so small, it doesn't matter next to 0.2. So imagine this. If you have 1 and you add 0.5 to it, does that matter?
Yes.
If you have 1 and you add 0.000002 to it, does that addition matter?
No.
Not really. It depends on how accurate we want to be, right? This is an approximation, so we're inherently introducing some error.
I think my question is, if we're going to assume the x is so small in that denominator bit that it doesn't affect 0.2 a whole lot, within the context of that whole equation, wouldn't the x's above also be the same?
Yes. However, a 1 plus 0.000002, the 1 dominates. 0 plus 0.000002, that 0.00002 is big compared to 0. So it's the fact that the subtraction happening here, we'll look at it, let's get an answer for this, and then we can look at it with numbers, and it might make more sense when we have specific numbers for this. So I'm going to go ahead, I'm going to keep doing this work in orange over here. So we're going to have 4x cubed. Since it's approximate work, I want to recognize that. 0.2 squared is 0.04. 0.04 is equal to 4.2 times 10 to the minus 6 multiplied by 0.04 divided by 4, take the cube root. I can't do that in my head. I'm like so close. It's multiplied by 0.01, which is going to give us 4.2 times 10 to the minus 8. Take the cube root of 8. I can't do that in my head. So I'm going to do 4.2 times 10 to the minus 6. I'm going to multiply by 0.04. I'm going to divide by 4. And then I'm going to take the cube root. And I get an answer of and I get an answer. I get 3.47 times 10 to the minus 3. And I say, okay, is that reasonable? So in order to check if our approximation is good, right, what I can do is I can take this 3.476 times 10 to the minus 3. I can plug it back in and see if I get 4.26. I can see how close I am. Into that original equation in black without the approximation, I can see how close I get. That's kind of like what successive approximation does. Usually, what we do in this class is we're just going to say, look, if I take 0.2 and I subtract 0.003467, I get like 1.96. I'm going to do it twice. 0.003467. If I subtract 2x from 0.2, I get 1.93. Is that approximately the same as 0.2? We've introduced some error in doing this approximation, but we made the math way easier.
Say that last sentence one more time.
Okay.
I understand what you're saying when we got to the point of 3.47 times 10 to the negative 1.
Right, solving that equation.
Yes.
Now we're saying, okay, did this approximate work that we did in orange is it a good approximation or a bad approximation?
And how would you assume that without having to work it through?
We've got to work it through to check, right? So the easy way to check, in this class, depending on who you talk to, you just have a guideline for how much error you can tolerate. Some people are like 1% error is all I can tolerate. Some say 5% error. I'm like 10% error is fine, right? So as long as my approximate x is less than 1/10 of my initial concentration, that 0.2, close enough. Right? So I'm doing a kind of quick check in my head of like, if I multiply this by 10, it's still smaller than 0.2. So it's less than a 10% error. So that is how you would do it with the x is small approximation. And we're going to spend a lot of time talking about the x is small approximation with simpler examples than this as well.
So what you're saying is, if we get to the end of this, and 3.476 times 10 to the negative 3 is truly like way smaller than 0.2.
Good enough.
So now we can answer it?
Yeah, that's the answer.
But it's asking us for the concentration in molarity of all three.
Oh, right.
Yeah, that's where I'm stuck.
So,
I was like, what do I
plug back in here. 0.2 minus 2x, 2x, and x.
Okay.
Right, so the equilibrium, sorry, I forgot to finish the problem.
Okay.
Right, so once we have this x solved for, once we have this x, we can take this x, and my pen is dead. We can plug it in over there. So the concentration of S2 is just the x value, right? Because the concentration at equilibrium of S2 is x.
Okay.
The concentration of H2 at equilibrium is 2 times that x value, because there's that 2x for the equilibrium concentration of H2. Yeah, we're doing number 4.
So,
The concentration of H2S is the one that's a little bit tricky, because it's 0.2 minus all this other stuff. Did you get it to work on?
Yeah, but it wasn't coming out to the answer that I got.
Let's see how close it is.
I got
I got an extremely big number for 3.
so did I. And I thought it was wrong, but it was right.
It's wrong, but then
Mine's like 34.
Let me
I'm
make sure.
not
Yeah,
sure.
same.
This might
And I
work.
put it in there, and it was right, and I was like, walk away, walk away.
Exactly.
Yeah, but I,
looked at that and I was like, I got it wrong. And I put it in and I was like, oh, I got it right.
yeah, same.
17.
You notice your x value that it solved for. Scroll down a little bit further.
It's wrong.
So,
0.00013. Wow. What is that? 1.3 times 10 to the minus 3? So we introduced a bit of error.
Yeah.
so when I input the value we got for x,
Yeah.
twice that as the molarity of H2,
Mm-hmm.
it's saying error processing your input.
Oh, let me
Yeah,
see
just
how
start with
you
100
probably
grams.
just have a typo
More
in
mass.
how it's
And
expecting to
it's
read it.
Yeah, I
The
just
more
tried,
you
I
show.
put the x value in as well,
Oh, yeah,
and then
that's
just
what
cleared
it
it out a
is.
moment ago. But, do I have to put molar?
No. Let's see, H2S.
So H,
Try putting all 3 in, because it's
Okay.
saying, so the error it's giving you is it's saying, hey, you don't have a first answer in there.
oh, okay, so
It's
then,
trying to put a number, if you want to check, so LabPow often needs all 3 inputs in order to evaluate.
okay,
So if you wanted to check, you could just put in 1s for the other things, but then it might just tell you your first thing is wrong.
okay. So for H2S, we just need to do,
0.2 minus 2x.
okay,
So our Mathematica solver gave us a number that was pretty different from this. So we are actually introducing error by doing this approximation. And it's more error than I was expecting. But, you know, it accepted the approximations that way. So,
I have a general question.
Sure.
My name is Diego, by the way.
hey,
Just like regarding Chem 3, is it mostly like just closing it all off, like review? You said we were reviewing Chem 1, 2.
yeah.
Because like I
So-
noticed that for Chem 2 we didn't really review at all. We just moved on right into.
Yeah, so this is as I said on the first day, and also I'm recording, but like, as I said on the first day, this is really the end of your year-long chemistry class. We're putting the stuff from the other 2 classes together in new and interesting ways.
Yeah, is that why not a lot of students need to take this Chem 3 and then move on right into OChem? Or?
It depends on what they are trying to do with their degree, right? So this, if you only need to do the survey of OChem, where you're just like, I need to know OChem exists, you can move on without this class. If you are going to be in a profession where you actually need to have a better understanding of organic chemistry, you've taken the full year of organic chemistry, they really like you to have this class for all of the acid-base stuff, the buffer making that we're doing.
Thank you.
Yeah, you bet. Okay, so that's number 5. We are introducing error by using the x is small approximation. We could do less error if we just solved it explicitly, but we have to solve a cubic equation to do that. Or we could use another approximation, successive approximation. We might get less error doing it that way, but there's going to be error unless we're solving it explicitly. Number 5 is approximately the same. It's the same idea, same process. So I think I'll let you try that one on your own. We can come back to it if there's more time at the end. But let's look at number 14. That was your question, right? Okay. So let's take a look at number 14.
I see tables again, but I just don't know how to set it up with what they give us.
Okay.
Because it's like, it's
I
weird.
got stuck on shutting it up.
Let's see number 14.
On my computer.
Okay, so same process to start, right? We're going to do our explicit versus implicit information, all of that. Consider the reaction of indium with cadmium to cadmium and indium with some equilibrium constant given. We make up 150 milliliters of a solution of cadmium nitrate with a concentration and a 10.6 gram chunk of indium metal. What's the equilibrium concentration of indium ions? Watts. Okay, so let's go ahead, keep that pointing towards me just for a moment. Let's go ahead, let's write down the explicit information. We're told it's 2 indium solid plus 3 cadmium 2 plus aqueous goes to 3 cadmium solid plus 2 indium 3 plus. We are told an initial concentration of cadmium is 0.148 molarity.
Say that again?
We're told the initial concentration, you might have a different random number.
Oh, I do, okay.
Yeah, so the numbers might be differently randomized for
So
you.
when it says that, because it says like, when they say that molarity, it's like for cadmium nitrate,
Ah, yes, okay.
which is why
So-
I'm stuck.
So let's look at what this is. This isn't for cadmium, this is for cadmium nitrate.
Where
So,
did the nitrate come into all this?
yeah, so let's go ahead, let's keep writing down the explicit things, and then we'll talk about the implied things afterwards. So then we're told 150 milliliters of 0.148 molarity CdNO3 2.
So as I'm following along, I can just input my number?
Yeah.
Okay.
And then we've got 10.6 grams and we've also got a K value given to us of 9.01 times 10 to the minus 4. I think that's all the explicit information. Okay, here's the explicit information. We got a K value, we got a reaction, we got a volume, a concentration, and we got some solid. And the thing we have to do is we have to say, okay, well, what's the implied information inside of here to get to, oh, and we also know what we're trying to get to. We want to find what's the indium concentration at equilibrium. Yeah?
Yeah, except it's 3 plus.
Oh, it's 3 plus? Oh, it's 3 plus. 3, 3, 2, 2. Yep, 3. Okay. Wanted to make sure I didn't mess up my balancing coefficients with that too. Okay. We want to find our indium concentration at equilibrium. So let's start with thinking about, I always like to think for the implied information, thinking about what's chemically happening in the solution, what's actually going on. This is a redox reaction, right? I can see something losing electrons, something gaining electrons. It's happening in a 2 to 3 ratio. Some number of moles. This is a lot of indium metal, so I think there's going to be excess indium. Cadmium's going to be the limiting reactant just by the fact that it's milliliters versus grams. I think that's going to be the limiting reactant. Essentially what's going to happen is the cadmium is going to rip apart some of that indium by stealing its electrons. It's going to form cadmium solid, and indium is going to go into solution. Since my K value, and I'll put my subscript on there again, since my KEQ is a small value, I think this is only going to happen a little bit, but it's going to happen some. Technically, we could go to like standard reduction potentials, calculate knee cell, blah, 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 but we're given a K value. We don't need to do that. We just need to set up, I'm looking at this, I'm looking at initial information given, equilibrium question. That's going to be an equilibrium table, right? The fact that it gives me those things. Now, One of the weird parts is that you were asking about, it gives us cadmium nitrate. Nitrate compounds are?
Soluble,
They're always soluble.
always.
So the cadmium nitrate is just going to go to cadmium 2 plus. And that nitrate is just going to be a spectator ion. Okay, so the fact that it's a cadmium solution means that we could calculate the number of moles we have, but essentially right, however much cadmium nitrate I put in, I get that same amount of cadmium. It's a 1-to-1 ratio between the cadmium nitrate and the cadmium. I'm going to get twice as much nitrate, number 14 from 0. Which class?
I'm in 124.
Okay,
so
we'll get to that in just a moment. So we've got this, right, because it's a 1-to-1 ratio for the cadmium nitrate to cadmium, every mole of cadmium nitrate is going to be a mole of cadmium ions in solution, so that concentration is going to be the same.
So we're not concerned that there are 2 moles of nitrate on the right because we're not looking
Spectator,
at it. It's
yeah.
a spectator.
Spectator.
Yeah.
Now, technically, we do have to be a little bit careful when we're doing, like, chemically speaking. Nitrates are pretty good oxidizing agents. So the possibility for creating an unintended side reaction is something we might want to think about if we were doing this, like, in lab. Because there are certain places in lab this quarter where it's like, don't use nitrates. They react weird. And you have to use these other weird compounds. But in this situation, yeah, no, we don't need to worry about that. We can just go ahead and say, look, this 1.48 moles of cadmium nitrate is going to give us 0.148 molarity cadmium 2 plus. Now I can go ahead and I can set up my equilibrium table for this, which is going to be 2 indium solid plus 3 cadmium 2 plus going to 3 cadmium solid plus 2 indium 3 plus. I'm not going to worry about the solids. Technically, there's a time when we need to worry about the solids, but I don't think this is one of them. I'm going to have 0.148 there, and 0 there. That's my initial. My change is going to be minus x plus. Oh, ha ha ha! What did I do wrong?
Wait a second. Sorry, I got all the way to there. We are not worrying about the indium solid or the cadmium solid. Is that correct?
Correct.
Okay, that's nice. Yeah.
We don't include solids in the equilibrium table.
So we're not worried about the solid. Our concentration of cadmium is the same as the concentration of cadmium nitrate, which is 0.148. Then we're not worried about the cadmium solid. And we have a 0 concentration of indium because we're at the very beginning. But then we gain 2x.
Products of a reactants, indium 3 plus squared, cadmium 2 plus cubed, at equilibrium. Now, this is again going to be one of those situations where we end up with some messy math. I'm going to end up with 1.48 minus 3x cubed, so I'm going to get a cubed equation on bottom. And I'm going to end up with 2x squared on top. So I'm going to end up with another cubic equation to solve. So again, we go to our 3 possibilities. Successive approximation if we got some time and some scrap paper to go through. X is small approximation or online solver. Now, X is small approximation. I'm a little bit worried about the X is small approximation in this case. Because that K value is not really, really small. It's just kind of small.
So like when I did the x is small and I got 8.54 times 10 to the negative 4.
Uh-huh.
So.
Oh, that's okay.
Okay.
That's small enough.
Okay.
I was just worried because I couldn't do the math in my head. But if you did the math and you got that value, I think that's okay.
Okay.
Let's go ahead and do it together. Oh, check it and make sure it's okay.
we get to this point, we're putting the KEQ 9.01 times 10 to the negative fourth equals to the concentration.
Yeah, so I can start plugging these numbers in. I can do the 9.01 times 10 to the minus 4 is equal to 2x squared on top
Yeah.
and 0.148 minus 3x cubed on bottom. And so this equation in black is where I'm looking at it and I'm like, oh, it's a cubic equation. I don't like cubic equations. So I'm going to go ahead and use the x is small approximation, hoping it's okay. I'm worried it's not going to be okay because my KEQ value is not super, super small. It's kind of small, right? 10 to the minus 4 is pretty small. But someone else already solved the problem and they said it works, so we're going to try it and we'll see how we can check it at the end. So I'm going to say this, approximately 0.148. Look at how much easier this is going to make the math. 9.01 times 10 to the minus 4 is equal to 4x squared over 0.148 cubed. That is so much easier to solve. Okay. That is so much easier to solve. No cubic equation. I multiply two numbers by each other, divide by 4, take the square root. So much easier to solve. And hopefully it's a reasonable value. So I'll go ahead and take my calculator and I'll do this calculation with all of you. Hopefully we're getting similar values. 9.01 times 10 minus 4.
I think I forgot that my numbers are different.
Oh yeah, that would mess you up.
We're taking them
Square root. Yeah, so you might have different numbers. Watch out for that. I got 8.54 times 10 to the minus 4.
Yeah.
So what do I compare? That's my molarity. What do I compare to say if this is a good approximation, if this x is small or not? The two things I compare for this approximation, I've used all of my colors. I'm going to use a different color. I'm going to compare my x value to the initial concentration where I want to ignore my x value. That's what I'm going to compare. And I'm going to say, is x bigger or smaller than that initial concentration value? Not only is it smaller, but is it much, much smaller? And my rule, as long as it's, a tenth as big, close enough to being good. Some people will say a 20th is big because they want that 5% error. Some people will say a 100th is big. Any of you going into the medical field,
Yeah.
1% error for you. Not during this class, but in the future.
1% please.
Yeah, in the future, like 10% Gen Chem, 10% error, I'm okay with it. Future situations, like especially in the medical fields, there are certain things we'll learn this quarter, and I'll warn you when they come up, where you get something a little bit different when you take later classes in the medical field because they can't handle the error. I mean, 10% error can kill somebody.
We're not assuming the x in the
So.
numerator is 0.
No, it's just
Okay.
to make our math easier.
Okay.
Yeah, it's only the x that's being added or subtracted to something we can ignore.
Because we can see, okay.
And it's not that it's 0, it's just it's small by comparison.
So we just kind of cancel it out, ignore it for the moment. And
Right,
then
just
check it.
while we're making our math easier. Okay, so that's all the problems I have listed for now. I'm going to go ahead and pause recording while we collect some more problems to work on. So we've got some other questions to look at. Number 15, which is really similar to the one we just solved, number 14, except the x is small approximation fails, so we have to do it a different way. Bum, bum, bum. Let's look at that together. And there's actually, I really like this one because there's a really elegant way to solve this one. That just is like, so nice. So this one is, we have an initial concentration of some compound A and some compound B with no compound C. We want to know the equilibrium concentration of compound C. We've got this chemical reaction given to us. So let's write down the explicit information as we do. Number 15, we've got A plus B going to 2C with an equilibrium constant of 80.1. An equilibrium constant bigger than 1, ooh, excess small is probably going to fail in that situation. We have an initial A concentration of 0.407, an initial B concentration of 0.407, and 0 C concentration. And that's all the information we're given, and we're asked to find the concentration of A, B, and C at equilibrium. You notice I've already started, we've done a couple of these problems today, so I've already started organizing my information as I get my explicit information. I've already kind of started doing my equilibrium table. I can start doing my change. The fact that it's giving me initial concentrations, asking for equilibrium values, that's, you know, that's the key terms that give us an idea that we're doing some equilibrium calculation. And one of the things that's going to be really important in 129 this quarter is noticing what terms or what setup in a problem points us to a process. Because so many, I'm sorry about this in advance, so many of our problems are slight variations of the same thing that we have to really carefully look for those key terms in order to figure out which slightly different process we're doing. So looking for those terms. My change is going to be minus x plus 2x. I'm going to have 0.407 minus, whoa, that's not how you draw next, minus x, 0.407 minus x, and 2x. I'm going to go ahead and set up my KEQ is equal to concentration of C squared divided by the concentration of A times the concentration of B. I can go ahead and plug my things in. Get me to 80.1 is equal to 4x squared divided by 0.407 minus x. Now there's something nice that happens here. Since it's the same number twice, I can just write this down as 0.407 minus x squared. And this is where most people try to use the excess small approximation. And every time I've thought about using the excess small approximation, I've always looked at my equilibrium constant and thought, do I think x is going to be big or small before I try to use it? And anytime the equilibrium constant is a very small number compared to initial concentration, anytime the k value is really small, I'm like, we're probably okay. Really small means a lot less than 1. Here, our equilibrium constant is 80. It's bigger than 1, which means I think this reaction is going to happen a lot. X is not going to be small. If we tried to use the excess small approximation, what happens? You get a negative concentration for your A and your B. You just get nonsense. So, a couple different ways we could go about it. Question?
I have a question. Isn't there also an instance where you have to switch the signs? Like I remember sometimes if you which is like really confusing. Like sometimes you get
if a reaction goes backwards, right?
Yeah.
So if a reaction, we're going to have a different way we deal with that this quarter. But yeah, so if we looked at this and the reaction was proceeding in the reverse direction, you'd have to have your minuses and pluses changed. I always do it a little bit of a different way. I do the cognitive process at the beginning of the process rather than in the middle of doing the math.
Okay.
But yeah, there's another place where you have to worry about that. Other question? No, another question.
Could we square root all of it?
Yes, that's the trick. So if I rewrite this,
Facts. To make it go away.
yeah, so if I rewrite this as 2x squared, we get this nice little trick where I can just take the square root of both sides. And now I can just solve for x. Way easier, no approximation needed. Didn't need to pull up the online calculator, didn't need to do a successive approximation. We can simplify the squares. This only worked, and this problem specifically has this set up because the concentrations, the initial concentrations were the same value, and it was a 1-to-2 ratio to the products. So it was set up to make that work, to show us that cute little trick we could do. Now, do we have that happen really often when we're solving problems in the real world? No, but it's a good thing to look for. If we're in a lab setting where we are setting up our own chemical experiments, we can set it up so this happens. Now, I'll let everyone finish solving that. We're going to get some value for x, and that value for x should work without giving us negative concentrations. Hey, what's up?
Still not getting it.
Really?
I don't know what it is.
I'm not even getting it to get rid of that denominator. I just.
Okay, so that's how we solved that one. Everyone was able to go through the math, get the right value. What value of x did we get on this one?
Oh, yeah. So here.
So you just type in C4.
I had different numbers.
Ah, well, let's not worry about that.
Yeah.
Let's go ahead and look at number 11 then. Okay, so 11 is interesting. It's asking us to think about the Le Chatelier's principle and how changing different things will disturb the equilibrium and how the system will respond to reestablish equilibrium. So the chemical reaction we're looking at here is CH3CO2H, which is a weird way to write that, goes to H plus CH3CO minus. I'm going to write this the way I like to write it. This is acetic acid. I like to write it the COO way because that gives us an idea of the Lewis structure. And then it asks several questions. The first one is, so we want to know what happens when we do different things to affect the equilibrium. If we add water to the beaker, so adding water to the beaker is going to decrease the concentration of everything, kind of uniformly. That's not going to really have much effect, but we have an asymmetry. We've got two things over here and one thing over here. So that is going to affect the equilibrium. If we look at the KEQ associated with this, products over reactants, I'm going to go ahead and write this as
Wait, can I ask
H2O+.
why it actually makes a difference?
Yeah.
Like I was thinking if we add water, nothing would happen since it's a covalent bond, so it doesn't.
Yeah, let's look at this together and understand why this happens. CH3COOH. So if we add water, keep in mind, this is molarity over volume, molarity over volume, molarity over volume. So let me go ahead and we'll do a silly little thing real quick. Right, this is going to be the moles, H plus. I just opened a different tab. I hope I didn't close your tab. No, there it is. Okay. So we got moles of H3O plus over volume. We got moles CH3COO minus over volume. And then we've got all that. We've got moles CH3COOH over volume. If we add water, we're going to do like +2, +2, +2. Right? Since it's affecting the top twice and the bottom once, it's going to be uneven in the way the volume affects it. So that's what's happening with that first one, where you would think adding deionized water doesn't affect it, but because it's two things are getting diluted here and only one thing's getting diluted here, it actually does have a little impact on the equilibrium.
So it's gonna shift left, right, to try to overcome that?
Yeah.
Okay.
So really, could you just repeat again where we got the H3O?
Oh, it just turns out that is H plus versus H3O plus. It turns out H3O plus is more scientifically correct. But we haven't done the Bronsted-Lowry definition of acids and bases yet, so I'll just leave it as H plus for now. It bothers me, but since we haven't learned the right way to do it yet,
I
I'll
thought
just
I
leave it
missed
there.
something.
No, I get so sick of writing H plus when it's not really scientifically accurate.
He had just said that it shifts left in
Oh.
that situation, but it shifts right.
Yeah, I sorry, I said yes without thinking through it. So let's think through it rather than just me just saying yes. The side that's getting more diluted is the side with more things. So we need to push things
Yeah.
back towards that so it's going to shift right.
Yeah.
Sorry, I should have thought through it before I just said yes.
Yeah. That makes sense.
The second one is add a few drops. The second one's easier. Adding HCl. Now, HCl is a strong acid. It's going to disassociate. So number one is going to be shifting towards products to try and deal with that extra dilution happening on the product side. HCl is going to be a strong acid. It's pretty much just like adding H+. Cl minus the spectator ion. If you add products, it's going to shift back over. Right? You're adding products. It's going to shift back towards reactants to trying to reestablish equilibrium. Adding some potassium acetate, and it's got a note that salt is quite soluble. So that acetate is essentially just adding products. You're adding acetate anions.
So it'll shift
That's
towards
also going to
reactants?
shift it towards reactants.
So everything that like breaks apart is considered a product that you're adding?
No, it just happens. So let's do another one. So that's adding potassium acetate. What if I added potassium chloride?
That'd be a reactant.
Is there any potassium? Is there any chloride?
Oh, no.
It doesn't do anything.
So it's
Right.
only if it attaches to some.
Yeah, so the reason potassium acetate affects it is because I'm adding an ion that's already, I'm adding a
acetate.
product, the acetate anion that I'm adding in. This is acetate. So I'm adding a particular product, and that's what makes it shift.
The reactant side too?
It's bonded on the reactant side.
so it's not
There's acetic
just-
acid on the reactant side. So adding acetate will take up extra H+ out of solution to form more acetic acid to reestablish equilibrium.
Where does you have the moles of H+ over V + 2?
The +2 is like a generic, let's just increase the volume a little bit.
Oh, okay.
And so that was to show that like if we increase the volume a little bit, it affects the product side more than the reactant side. Then we add some potassium hydroxide.
Is that, wouldn't that split up into like K plus OH minus and then react with the H plus?
Yeah, so we do our thought process. It's going to split up into K plus and OH minus. There's no K plus, there's no OH minus, so it's not what we would call a common ion effect because I'm not adding something that's already there. But there's a side reaction that occurs because the OH minus can react with the H plus
For water?
to make water. So essentially adding hydroxide is removing H plus from solution. What's this going to do if you remove H plus from solution?
You're gonna make more of it.
You're going to have to shift back towards products to replace that H plus you're removing. So we're going to spend some more time in class talking about Le Chatelier's principle, looking at some examples like that. That's a great example to get our brains thinking about something we hopefully remember from 128 a little bit.